Everybody, welcome back. Last time we described how to calculate the rotation matrix using a set of angular rotations about x, y, and z axes, and how we could use any combination of rotations, either x, y, or z, in any order to achieve a three-dimensional rotation of a coordinate system in space. This time we're going to talk about how do we actually take a coordinate system defined in three-dimensional space and calculate the rotations or the angles of that system. Because again, most of the time we want to be able to describe things in angles that are easier to understand than a 3x3 orthogonal matrix. So again, keeping in mind that this is going to be dependent on the order that we use for calculating the angle values, the actual rotational matrix itself is independent of the order. But when we calculate theta 1, theta 2, theta 3, or theta x, theta y, theta z, it's going to be a function of which orders we use. And we'll go into that more in just a little bit, right? Again, you can also see the examples for this following along in the book. We're going to use a different set of values than given in the book, but the process is basically the same. So what do we do here, right? So for simplicity, what we're going to do is we're actually going to track a single frame, and we're going to say that the anatomical frame and the marker frame are the same frame. So we're not going to calculate a difference in orientation between the tracked frame using the markers and the anatomical, or basically the bones, right, inside the system that's being tracked, right? Also today we're going to use the markers defined on the shoulder, the elbow, and the wrist to track the upper arm segment. The book gives another example of tracking using more arbitrary markers, but again, you can use any markers you want as long as you have a reasonable way of identifying where the anatomy is based off the marker positions. So this is the book's basic process. This is what they use going through it. First, they define a global axis. So you have your global axis, which is like your x, y, z of the frame, right, of the lab frame. And then we have our markers, which are being tracked in real time, right, or being recorded, however you're working. And we have a transformation matrix that describes the marker axes, right, relative to the global axes. So you see here there's an xm, ym, zm, and that allows the markers to be placed arbitrarily at any location on the segment that's being tracked. Then we also have a set of calibration points which are used to calculate the anatomical landmarks, right? So this is also an axis relative to the segment that's being tracked, and it's attached to that segment, and we're assuming it's rigid. So there's not going to be any movement between the anatomical axis and the marker axes. So if I know the rotation, right, from the global to the marker frame and the rotation of the marker frame to the anatomical axis, we can calculate the global to the anatomical axis by setting this marker to anatomical axis as constant, right? And so then I only need to track the markers, and I can figure out what my angles of each segment are going to be. Now, the disadvantage of this is it takes a little bit of extra math. The advantage to it is that, again, our markers don't need to be placed at anatomical landmarks, so we can put them kind of wherever it's convenient. And we can have many extra markers that are used to calculate kind of multiple marker axes, and then take the kind of the best value of those, or even use something like a single value decomposition to figure out, what the best fit of a anatomical axis is to those marker points. In this class, to keep things simple, we're going to basically skip this second part, and we're just going to assume that the marker axis is equal to the anatomical axis, right? And so this allows us to go straight from global to anatomical axis, right? And then we can go from that matrix here straight to our joint angles. So just to keep things simple, again, keep in mind you can have multiple transformations to get to these any way you want, but for the purposes of this class, just to keep things a little bit easier, we're going to go straight from however our coordinate system in the lab is defined to however we want to define our anatomical frame using markers placed at anatomical landmarks. So keeping that in mind, let's take a look at our example. We're going to use the markers on the shoulder, elbow, and the wrist to track the upper arm, and we need to define our anatomical axis based off those marker positions. So we're going to have the z-axis, we're going to start with the x-axis. The x-axis of the anatomical frame is going to be aligned with the vector from the shoulder to the elbow. So again, from the shoulder to the elbow. So again, we have our x-axis here. Again, we just need a unit vector that's parallel with that. So we'll take that vector from the shoulder to the elbow, divide by its magnitude here, and then we get a vector for the x-axis. And then for the y-axis, what we're going to do is we're going to take a vector that's perpendicular to the vector for my x-axis, as well as the vector from the elbow to the wrist. So to get a vector that's perpendicular with any two vectors, all we have to do is take the cross product, right? So in this case, I have the vector from the elbow to the wrist crossed with the vector from the shoulder to the elbow. Again, that gives me another vector which is orthogonal or perpendicular to both of those vectors. And that's important because that's going to make this next axis perpendicular to my x-axis, which is what we need for an orthogonal frame. So we have that. I'm going to save this as a temporary vector. And I divide that temporary vector by its magnitude, and we get our y-axis. And the last thing we need to do is we need to get the z-axis. So here I have my z-axis. I'm going to calculate this by doing the cross product of the x and the y-axes. And because those are both orthogonal unit vectors, the resulting vector will also be a orthogonal unit vector, right? And doing all that for time is equal to 0. So let's take a look and see what this looks like in MATLAB, because we've already kind of gone through enough of this inside the presentation. We want to see how we're going to apply it. So I'm going to go to MATLAB and show my script. So this is the script you guys have posted on Canvas for this section of the virtual lecture. So inside here, we have our shoulder, elbow, and wrist defined for times t is equal to negative 0.005, t is equal to 0, and t is equal to positive 0.005, so 3 time points. I also have the rotational vectors here, or matrices here. You don't need those, but I just wanted to include them as a reference. And then kind of some guidance in terms of comments to help guide you through this process. So first, let's define the vector from the shoulder to the elbow. So I'm going to say SE is equal to E minus S. And because these are given as matrices, I don't have to do this in any kind of a loop. I can just basically do it for all the time frames at once. And that'll be true for anything that's just an element by element operation. And for things that are not an element by element operation, you just need to define, you want to do the dot product or the dot division where appropriate. And again, it's usually a good idea to kind of run through that and make sure it's calculating values that make sense to you as you're going through. The next thing we'll do is we'll find the magnitude. We'll divide by the magnitude to get the x-axis. So the UAX is equal to the vector from the shoulder to the elbow divided by the magnitude of the vector. So I'm going to do the square root of the sum of the shoulder to elbow vector dot squared. And let's go through each of those components kind of one by one. So if I do the dot square, the dot square of the vector, I get the square of each of the elements, right? If I were to do just the regular square, right, I do the matrix times the matrix and I get a different value. So again, keep in mind that those are different things. The dot square is the square of the elements, and then the square is the matrix times the matrix. But again, I want the square of the elements because I want to do the square root of the sum of the x, y, and z components. So the dot square is the one I want, and then I need to do the sum of those squares. So I'm going to do the sum of SC dot squared. And you notice here they actually gave me a row vector, right, which was the sum of the columns, which is not what I want. I actually want a column vector, which is this, which is the sum of the columns, as opposed to this, the sum of the rows. Sorry, the column vector that is the sum of the rows, because the rows represent the x, y, and z values. So I'm going to use the comma 2 annotation to include this as the sum of each of the rows. So again, we have the length, trying to get the length of the SE vector at times negative 0.005, 0, and positive 0.005. And then finally we need to do the square root of that. So square root of that value. And so that's actually the length of the vector from the shoulder to the elbow for this participant. And that looks reasonable. It's about 1/4 of a meter. So that looks good. So now I've got that math right. It's okay. That's how I want it to look. The only thing I'm missing here is on my sum, I need to do dot comma 2. And then I can suppress that output because I'm pretty confident that one's going to be working. Right, and I can run it again just to make sure I don't get any deletions. Oh, I did get a deleting. So again, I want to use the dot division here because these are not matrices of the same size. So we'll try to run that one more time. Good. So now we're working. We can clear our screen just so we can move on to the next spot without worrying about the previous one. For this next one, for the y-axis, I'm going to start by defining the vector from the elbow to the wrist. So we'll do wrist minus elbow. Again, just kind of following along with the same process we used inside the presentation here. So again, if you want to follow along the presentation, the next thing we're going to calculate the perpendicular vector by doing the cross product of the elbow to the wrist and the shoulder to the elbow. So we'll do a y temporary, y temp. We'll make it equal to the cross product of the, let me try to move this way we can see them both at the same time. Almost. Of the elbow to the wrist and the shoulder to the elbow. And because this one uses the same kind of method as the previous one, as the sum, to define which direction we want to do this in, we want to use the comma 2 as well. And we can show what that looks like inside here. We just don't have the elbow defined. Let's run it once. So again, if we do the cross product in the second direction, that's the value we get. And you see we have pretty constant values for the x, y, and z components, which makes sense. If we were to do this without using that comma 2, we get kind of a bunch of variation that doesn't make a lot of sense for the values that we're using, right? So again, keeping track of the different orders. If you're doing this frame by frame using the loop, which we'll cover in a little bit, you don't have to worry about that quite as much. But again, it's important to know how MATLAB handles that syntax. And then we need to divide by the sum to get our y-axis. So we'll do our UAY equal to our temporary. And I'll use the exact same method I used here by copying and pasting it, because we already checked to make sure that that works for calculating the magnitude and dividing. So again, if we know that works, good. We can run it and make sure we don't get any blings. And we've got our y-axis, so we can clear that out. And the last thing we need is get our z-axis. So again, our z, all we have to do is take the cross product of the x and the y. So we'll say our UAZ is equal to the cross of UAX, comma, UAY, comma, 2. Again, we're using that 2 to specify the direction that we're using for the cross product. So we can save that. And again, we'll just unsuppress that and run it and check and make sure those values make sense. And again, this is the z-axis at, you know, kind of the first time, second time, third time. So there's a little bit of variation there, but it's, you know, reasonably constant, which makes sense because again, these are time points that are fairly close together, right? All right, now that we've got our UAX, UAY, UAZ in MATLAB, let's go back to the presentation and figure out what we're supposed to do with those. So here we've got our X, Y, and Z. And we can use those to figure out what our rotational matrix should look like, because we have our X component, right, of our UAX, our component on the X, Y, and Z axes of our lab frame. And then the same thing for UAY and UAZ. And we see that those become the rows of our rotational matrix. So again, if we look at our first row here, it's our X prime on X, X prime on Y, X prime on Z. Well, that's the X-axis of our upper arm frame as we described it, right? So what we can do is we can just basically stack each of these rows on top of each other for each time to get our rotational matrix at each time period. So let's do that. So first thing I'm going to do is I'm going to make a for loop. I'm going to do this for 1 to 3 because I have 3 time points here. I'll make a note for each time step. Right, we want to define the rotational matrix. So I'm going to say that R, and I need to make sure I specify the size of R, because what I'm doing now is I'm making a 3-dimensional array. So I'm going to say all the rows, all the columns of R at the ith kind of page, right? So it's kind of the depth of the array. I'm going to say that's equal to our UAX, UAY, and UAZ. So again, I'm using the semicolon to separate rows. So I have a next row every time I do that. And if I want to make this look a little bit more consistent with how it's actually being used, I can use a hard return as well, or instead of that, to define the matrix. Right? Then we got to make sure that we put an end on this. I'm going to add some more things inside this loop in a minute, but I want to check and make sure that that is working before I move on. So when I run that out, oh, I got a ding, which means I did something wrong, right? Oh, I forgot to say I. So for I is equal to 1 to 3. Got to specify what the index we're actually using for the for loop. No ding there. All right, so let's take a look at our results. And we should be able to see that if we use our R of all, comma, 2. Oh, that's not right. Let's try clearing. Clear all. I'm trying running this one more time. Probably because when I ran it the first time, I didn't have that for loop defined properly, and that's what gave me the error. So I'm just going to clear off the workspace and then look at it again. Oh, that's the cross product. Let's just do CLC. So R. Still not right. I know what I have to do. I forgot to index the time positions of X, Y, and Z. So what we want is we want UAX at the first instance. So each the first row, all the values. The ith row, all the values. Z, ith row, all the values. Right. So we need to make sure that we're actually saying, okay, this is the rotation matrix at time I, right, or at frame I. And then we take the X at frame I, the Y at frame I, and the Z at frame I, and use that to compose our matrix. We're going to have to clear our workspace off, because we still have that kind of bad data there, so I'm just going to add that to the front. If we want to, we can also CLC on this, so we don't have to run a clear screen on our thing every time we run it too. You may or may not want that, because if you want to have things stay in your command window for your own purposes, then you can take that out. But so let's look at our R22, and we should be able to compare this value with the one that we calculated inside the presentation and make sure they're the same. So again, we have 0.9, 0.4, negative 0.4, 0.18, 0.29, 0.86, 0.42, negative 3.2, negative 3.2, and 0.89. So that looks good. Good. So we can move on to the next part. The next thing I want to do, and probably the last thing we'll do in this segment of the video, is use our rotational matrix to actually calculate the values of theta 1, theta 2, and theta 3. So in this case, I'm trying to move this out of the way. What we have here is a rotational matrix, and we have a rotational matrix as defined by the 3 rotations, our theta 1, theta 2, theta 3. And we can figure out what values of theta are required to make this matrix by basically just doing the trigonometry. So in this case, if we do the inverse sine of the third row first column, right, that's going to give us theta 2. Once we have theta 2, we can use that as well as the element at the third row second column right here, right, to figure out what theta 1 is. And then once we have theta 1, we can go back and look at theta 2 again and figure out what value we can get for theta 3. Now keep in mind, when I use inverse sine, this is going to return values between negative 90 and positive 90. So there's also a possibility that they could be in the second or the third quadrant. You got to use a little bit of your own kind of intuition, as well as just some mathematic checks. You can basically plug the values for this back into this matrix to make sure that it works. And then same thing here for sine, and then for cosine, it's going to return values from 0 to 180. So again, make sure that that makes sense and you're getting the correct values. If you're not, then just flip it. So I ran this before, and we actually got, it worked fine for the first two, but on the second one, the true value was actually negative 18 as opposed to positive 18. And again, I knew that was correct because it was giving me the wrong value for other elements in the array. And so let's take a look at that real quick in MATLAB. So I'm going to go back into my for loop. And here, so I'm going to use this to find the elements of the rotational matrix. Let's going to copy and paste that back in. Our comment. It wants to be there. That's fine. It's trying to do an automatic indentation, which is fine. So for theta 2, and I'm going to actually try and make theta into an array. So what I'm going to do is I'm going to say theta I comma 2. So this is theta at element or frame I, right? Because I'm using the row as my indices for the time. And then the column 2 is going to be the value. We'll do inverse sine. And I'm going to do it in degrees. And then this is the third row, first column. Again, it's the ith frame, so that's the frame that we're using. And then we can do our theta 2, or sorry, our theta 1, which we're calculating after we have theta 2. So again, we'll do theta 1. So again, the ith row, first column, and we're doing inverse sine of our r, and we're going to use the third row, second column in this case. And we're actually going to use negative of that. It's a positive on the example below just because it's a negative and a negative, so the negatives cancel, right? But if you replace this negative 0.32, which is our R32, it's not going to be a negative there, so we need to have that divided by cosine b, because again we have degrees of our theta 2, and we're showing theta 2 at the correct time, so theta 2 at the same time as we're calculating here. And that should balance our parentheses. So we have our theta 1 and theta 2. Now we just need our theta 3. I'm actually going to copy this because our next equation looks pretty similar to that. So our theta 3, we're going to use our inverse cosine. And we're doing this for our first row, right? Our first row, first column. Yeah, first row, first column. So R1, comma 1, comma I. We do want the ith element for each of these rotations. So again, this is the frame I, index 3, 1, frame I, index 3, 2, and then frame I, index 1, 1. Again, we're using our theta 2 as the denominator here in both of these. So that's going to give us our theta 1, theta 2, theta 3. So we can run that out. And we can see what this looks like. So if I do my R, or my theta 2 comma all, I give you my theta values for the time equals 0. And we can see that our theta 1 is 20, our theta 2 is negative 18 point that. And then look, our theta 3 is saying it is, oh, we change that, a cosine d. Did I use the right index? Let's see. So cosine theta 3, that is 1, 1. How do we get a different value? We got a different value for our last piece here. Oh, we have negative. Shouldn't be a negative, because again, we don't have a negative on that value. So take that negative back out, and I'm just going to run this again. And we'll take a look at our theta. Good. And then we can also, again, to check and make sure that this is correct, and again, we have the positive value instead of the negative value here, we can plug that back into our rotational matrix, right, and do that. Just to keep this video a little bit shorter, and have you guys take my word for it or check it on yourselves to make sure that this works, but we do need to put the negative value to get the opposite version of the cosine. And that'll give us the same theta as in the presentation there. All right, so that gives us all of our angles. Hopefully that was reasonably clear, and I'll come back soon with the last part of this for the virtual lecture.